Welcome to Func Prog Sweden, the last of the year for this year, and of course we'll be back next year, as always. First, I would like to welcome all our recurring viewers. Welcome back to Func Prog Sweden. And then I would like to welcome all new viewers of Func Prog Sweden. This is the meetup where we deep dive, shallow dive, go into functional programming, of course. And we cover all sorts of topics from Haskell, Super Haskell, Agda, and into C++, and you can do functional there. So check out our YouTube channel if you want to know more about functional programming. But now, over to today's agenda. First up, intro by me, Magnus. Then we'll do a better software design with domain modeling by Eric Normand. And then the second presentation, Go.js diagrams in PureScript by Andrea. That will be really interesting. It's like a combination of PureScript and JavaScript. What could possibly go wrong? Yes. Then I would also like to thank our video sponsor, Adabeat. Adabeat is an IT consultancy company based in Stockholm, with office in Stockholm and in Ho Chi Minh City, Vietnam, where Adabeat is a company that is focused on functional programming. And if you want to know more about Adabeat, head over to their webpage or check them out on social media. The schedule for the coming year then, 2024, we'll be back on the 16th of January with another meetup, and then of course we'll run one in February, March and onwards. We'll come back with the schedule, and if you want to know when, just go to the meetup page and you'll see when we announce them. And if you want to support the Func Prog Sweden community, head over to Meetup and make sure to follow us there. Follow us on YouTube. We also started a Discord server. If you want to ask more advanced questions, head over to Discord. You can ask all sorts of questions. And if you have questions during the presentation or on the presentation, you either ask them on the Discord server or you ask them in the YouTube chat. And I will read it up for the presenters. With that said, let's get started with the first presentation of the day. Welcome Eric to Func Prog Sweden.
It's really nice to be here.
Welcome, warm welcome. Yes, the stage is yours, Eric.
Okay.
Yeah.
Thank you so much, Magnus.
Yeah, you're welcome.
So my name is Eric Normand, and my presentation is called Better Software Design with Domain Modeling. I'm writing a book on domain modeling, and so these are a lot of the ideas that I'm going to be talking about. Can I get my slides up? Yeah, thank you. Cool. So one of the things that I notice when we talk about software design is that we often will try to give rules of thumb, some guidelines, some principles, but to me, they always fall short. Either you're already good at design, and so yes, they're helpful to remind you, but so then you don't really need them though, or you're not good at design and they don't really help, because at that point there's more exceptions than there are actual cases that follow the rule. So I'm trying to take a different approach to talk about software design from rules and guidelines and principles. And if I could summarize my talk in one line like this, it would be that if you want to do good design, you need to make good decisions, because software design is all about making software decisions. And if you want to make good decisions, then you need good information. So when I'm talking about decisions, I'm talking about everything. Like, I've looked for definitions of software design, and there's so many out there. It's basically every decision you have to make, from whether you are doing a for loop or a while loop, or how you structure your modules, all the way up to architectural decisions. All those things fall under this umbrella of software design. And it's basically just programming, right? Once you put it that way, it's just programming, but it's with this attitude that you are making conscious decisions. So in my book, I'm organizing the content into what I'm calling lenses. Each lens gives you a different perspective on your software and on your domain. And hopefully, if you get enough of those lenses together, you can make a full picture of your domain and the software that you need to write for your domain. I've got the book is still work in progress, but right now I've got 10 different lenses. And I don't have time to go over all of them today. So I'll just talk about three: the data lens, the operations lens, and the volatility lens. So let's start with data. So when I'm about to show something that probably everyone here can already do, but I'm going to go through it quickly so that I don't bore you. But the point is that we're going to go deeper into the actual mechanics of what we're doing. So if it looks like, yeah, I know how to do that, this is boring, like you're on the right track. It means I'm showing something that you know how to do, and we're going to go a little bit deeper, and it'll help explain what domain modeling is all about. Okay, so our domain is a coffee shop. This coffee shop makes coffees. It's sort of like a Starbucks. Okay, I think we all understand Starbucks. There's three sizes: super, mega, and galactic. There's three roasts: raw, burnt, and charcoal. And then there's all these add-ins that you can add to your coffee, like soy milk. You can have a shot of espresso, some hazelnut syrup, chocolate syrup, etc. Now, if I was going to model this, an order for a coffee in JSON, I would probably do something like this. I would have string representing the size, a string representing the roast, and an array of strings representing the add-ins. Now let's see how we got there, because this kind of just comes automatically to me. And it took a lot of time and introspection to figure out what I was actually doing to get those strings, to get this structure. Okay, let's just look at the size for now. Let's zoom in on this. So we have the three sizes, and they actually have a relationship between them. We can only have one size. A coffee can't be like large and small at the same time. So we have this one of relationship. And I'm calling that an alternative, meaning you have to choose one of these alternatives. And so then we give each alternative a name, a string, to represent it in our code. And then we need to maintain that same one of relationship between those strings. And so I'm going to use TypeScript here. We're just going to do a tiny bit of TypeScript. So if you don't understand TypeScript, that's fine. I'll explain everything. But we're defining a new type called size. And then we're saying it's either the string super, the string mega, or the string galactic. That's what those pipe symbols are. It just means or. Okay, now roast is going to be very similar. They have the same thing. You can only have one roast. So we have a one of. That's an alternative. We give each one a string, and then we want to maintain that same relationship between the strings. So we have a very similar type called roast. Now, this is going to come up a lot where you see something in your domain, you see a relationship, and you want to maintain that same structure of relationship in your code. All right, now add-ins are a little more complicated because we can have multiple ones. It's not one of. And still, we're going to do a one of. It's going to be like two different levels. So the first level is we need the one of, right? Like any particular add-in is one of these choices. So it's going to be an alternative. And so we'll do the same thing. I'll skip drawing the arrows and stuff just for space, but we'll have a similar kind of type there. But then we have this other relationship with the coffee is that you can have 0 or more add-ins. And that we'll call a collection instead of an alternative. And we'll just make it like this for now. Okay, so this just means define a new type add-ins that is an array of the add-in type we have up top. All right, now we need to combine all of these into one single coffee order. So what we want to say is that we have all of these, not one of, but all of them. We have a size, we have a roast, and we have a set of add-ins. So I'm calling these a combination because we're combining these things. And obviously we just went through this. Each one has its own type. And so now we can make a type for coffee, which has a size, a roast, and an array of add-ins. Okay, yes, that's pretty clear. All right, this should be pretty clear right now. This should be like pretty standard, like, we do this every day as programmers. But I want to go a little bit deeper now. So this is the size again. Same thing we saw before. And I'm going to draw a line here. Everything above the line is the model. It's the idea we have in our head of how this is supposed to work. And below that, we have code. Okay, so we've taken this model from our head and we've encoded it into our programming language. Above, we've found the relationship, and then we've made that an encoding for that. Okay, now I'm going to move that line up and like erase the picture. So we still have the same stuff, but it's at the top. And we're just going to look at all these different options we have for encoding. We chose one, which was this, it's called a union type in TypeScript. But we have other options. So that's the first one, the union type, strings with union type. We have string with enum. So we could define it like this. This is also valid TypeScript. And it has different semantics and different ergonomics to it. And then we have this other option that we could use JavaScript classes and a TypeScript interface. So we could define an interface that has a name. And then we can define 3 different classes, one for each size, super, mega, and galactic. And those classes could represent the same values, the instances of those classes. Okay, so I'm bringing this up because we have these choices when we're programming, just like we choose between for loops and while loops. We have these choices all the time for how we're going to encode the model. And we often forget to, we often have habits that just say, oh, I'm just going to use this because that's what I always use, or that's what I was taught. And if there's something I'm going to posit as like something I can't prove, it's that you get better design by evaluating more options, more encoding options. Okay, so we have these 3, but how do we evaluate them? Well, we have to use something. One thing we can use is a thing called fit. Okay, let's look just at the size and the roast because the add-ins complicate it a lot. So how many different kinds of coffee can you make with 3 sizes and 3 roasts? Well, we can all multiply. It's 9, right? And how many coffees can we make with this TypeScript type? Well, it's the same. We have the 9 different ones, one showing up at a time. There we go. So we have super and raw, super and burnt, super and charcoal, right? These correspond to those same things from the images before. So we have our model in green and our code in red. We have, and we're looking at size and roast, we're looking at 9 things that are both in the model and the code, and 0 things that are just in code. So in theory, you could have things that you can write that are valid in your type that don't correspond to anything that you've got in your head. And in theory also, there's things in your model that you can't write in code. Like your type won't allow it. So in this case, we have 0 unrepresentable things and 0 meaningless things. They're all, everything we can represent is in the intersection. And so this is perfect fit. This is where your model and your code correspond perfectly. Now let's look at another thing that we could have done, which I didn't mention before. To get perfect fit, we could also just say, well, we're just going to give each of these combinations of size and roast a number from 1 to 9. So we have 9 numbers and we have 9 coffees we can make. So that's perfect fit. So fit isn't everything, but fit can show you a lot. Let's look at a case where fit isn't perfect. So let's look at the add-ins. Because we've got 0 or more of 5 different choices, it's actually going to be kind of hard to figure out exactly how many there are. We can, you can basically list them out. You can do it on a computer really easily to count them. But we're just going to see how far we can get and whether we learn something from it. So we have 0 add-ins, so that's one possibility. We have 1 add-in, so that would be 5 more, so that's 6 total. If we have 2 add-ins, well, now we're talking about all these different combinations. But look at just writing some of them out, we can see that there's already kind of an issue that we have soy with espresso shot and espresso shot with soy. These are both representable. They look different. They're encoded differently, but they're basically the same coffee, right? It doesn't matter what order you mix those two into your coffee. Same for 3 add-ins, right? We've got soy twice and almond once, but we got all these different ways of writing that out. So even without counting them, we can see that, yes, we can represent everything. We have this intuition that, yeah, we got it. We can do everything we need. So that means 0 are unrepresentable. But we do have all these meaningless distinctions. So maybe this encoding of an array is not ideal. Can we find something that has fewer things that are meaningless? And so let's look for those things. Yeah, so this is less than perfect. Again, here's our add-ins. We're going to draw that same kind of line, and this time for collections. Let's just look at all the options we have, or some of the options. So we can use an array. That's what we've got already. We can use a set, except that won't work because we do want to be able to have duplicates, like 2 soys in our coffee. We can use an object. So that would be where we did something like this, where we had the key is the name of the add-in, and then the value is the number of times it's how many shots we put in there. And so now we can have 2 soys represented this way, 1 almond. And because in an object the order of keys doesn't matter, now we've gotten rid of that other problem too. So we've gotten rid of the ordering problem by doing this. But of course, now is a conundrum. Our key, like the type system, can't show us this. We can't use a type besides string in the key position. So now we do have to remember, we're gonna have to validate this, that we're not using the wrong keys at runtime. Okay, now let's compare the array and object, because both seem possible. We've got all these different things that we can express, and object seems to be winning so far. We could do a thing. It's important to know that, like, there's not going to be a clear winner, right? Nothing, it's never perfect. But one way we can mitigate the lack of perfection is by doing a normalization. So order didn't matter in the object, and we don't want order to matter. So we can do a thing in array where we always sort it, and that way we can compare them for equality. We just sort before we compare for equality, and that would get rid of the order dependence of an array. And here's another thing. We've opened up the door in objects that we have a soy 0. That's totally allowed by that type. And so we would have to normalize this too. Oops, sorry. Oh, went too far. We have to normalize this too by removing zeros and maybe even negative numbers, things like that. So both of them have their issues. So it's not an easy choice. I can't do audience interaction so easily, but right now, just think, what side are you on right now? Array or object? I'll let you think for a second. Okay. So another thing we can do, we looked at fit. We can also use other lenses to constrain. One of the advantages of having all these lenses is each one gives you a different perspective. And so if you can't figure out, if you have a lot of choices and they all look kind of similar, they're all valuable, but you can't figure out which one to choose, you can just look at from another perspective and see if one of the other perspectives gives you some insight. And we're going to do that in a second. But right now, what I want to kind of blow your mind a little bit while we're here. We'll have it all loaded. So this is that line I showed before. The size, we got on the top, we got the model. On the bottom, we got the code. Let's move it down instead of moving it up. We built this model, or we were given this model, let's say. Starbucks already had this model, and so we just used it. And, there's 3 sizes and there's alternative. But you can imagine a different model in the same domain of a coffee shop. Like, you could imagine them selling coffee by the volume, right? Like you say, I want, 40 milliliters of coffee, and they charge you per milliliter instead of these like discrete sizes. But in a more traditional coffee shop, the size is kind of dictated by the kind of drink you get. Each drink has a different cup style and size, and it's not really about like the small, medium, large. So I'm bringing this up to say that, like, one of the reasons software design is so hard is that we're not only trying to figure out how to code what we've got in our head, but we also have to experiment with the model that we've got in our head, and maybe a different model is more correct or more advantageous. So I'm trying to draw a diagram of the whole process of what we're doing. We got this domain, and we got to get it into code, and it's going to go through our heads because we're the ones programming it. So, sorry, I missed a T on that. Abstract is supposed to be. So we got this domain, and we're going to abstract it, meaning we're going to remove some details that don't matter, and develop a model of our domain. And then we need to encode that model into code. And then we can use the code. We rewrite the code, and we can play with it. And we see, okay, this one has a good fit for my model. This one doesn't. This one maybe is too slow. I need to change it. And so we can have this like feedback loop going on between encode and evaluate, figuring out the best way to encode it. But then we also might have to go back and revisit the domain and say, this whole model isn't working, and go back and abstract something else from it. Just trying to drill in how hard software design is. There's so many variables. All right, let's look at a different lens, operations. So at the coffee shop, the cashier has a touch screen that looks like this. They can select the size, the roast, and they can like click plus and minus on each of the add-ins. And right now the size is highlighted and the roast is highlighted. And we can see that they've already added some add-ins. Now, from this, we can look at what are the operations that they need to be able to do. They need to be able to set the size. So meaning when they touch super, it sets the size of the coffee to that. And I'm going to stop using TypeScript now because when you write a function with TypeScript, it starts to get really long and we don't need it. I just use my own little syntax. There's a comment at the end that just says that this returns a coffee. So set size takes a coffee and a size and it returns a coffee. We also have to set the roast. Also takes a coffee and a roast and returns a coffee. Oh, and this is functional programming. I don't have to mention, like, that's pretty commonly done, right? Where you have the current value and then you return a copy that's modified. And then we have to be able to add an add-in. So that will just increment it by 1. And remove an add-in will decrement. I wrote those out because I find that function signatures are like really great for representing these kinds of use cases. They've got the inputs, they've got an output, and they're like little easy to write. They're a little concise notation for it. Much better than something like in UML where you have like methods and arrows and stuff. Okay, so here's a function signature. It's actually what I should explain what I mean by it. It's got a name. It's got the arguments and their types, and you'll just have to infer the types based on the names, which I think we can all do. And then it's got a return type. So that's the 3 parts of the function signature. They're so concise and precise. They show you what, as long as you're talking about a pure function, they show you exactly what you're going to need to perform this operation, what you're going to get when you're done. And because of the name, it gives you also semantic hook because, you can also see that there might be some ways of implementing this function that just like return the same coffee without modifying it, like just ignore the size argument. But because set size, you know what it means. It's the right level of abstraction for reasoning. We don't want to start reasoning about the implementation yet, but we also want some token that's like a step towards implementation. Right, and we can easily implement this later. Very, very easy to see how to do that. I should mention another thing that I'm really into is instead of writing out your specs and stuff in something like UML, like we want to be moving toward code, right? And we want something formal enough that we can have some guarantees about it. And we want it to be a step toward implementation. All right. So here we have this problem where we are passing in a coffee that has size mega, and we're also passing in a size mega. So what should we do? Okay, I call it a problem. It's not a problem. It's a choice. There's a number of things we could do. We have a choice. We have to remember that while once we do the analysis, we might find that one choice is clearly a winner. We have to evaluate that. A good designer is always going to look at their choices and choose the best one. They're not just going to plow forward with the way they've always done it or the way they were taught. So what do we do? First, we got to look at our choices. So one choice is we can throw. There's some languages that do this for stuff like if you have a I think some languages like Tickle, for instance, if you try to set a value in a hash map and the key's already there, it throws an exception. And, you know, it's a choice. They made this choice. I don't think they're happy with the choice that they made, but we have this choice here. Now, of course, I don't think that that's a good choice. This is one of the only recommendations I'm going to make in how to code. We should be aiming for total functions, and I think this is a concept that is super important, and it hasn't really escaped the functional programming world, and I hope it does. So when we're looking for a total function where we have this behavior that could possibly throw an error, we can do three different things. One thing is, I should mention what total function is. It means the function has a valid return for all valid inputs. Okay. So any coffee, any size you pass in, as long as they're valid, they type check or whatever, validate, then you're going to get a valid coffee as a return value. But one thing we can do is we can augment the return value. So we have this case where it's kind of weird what to do. We can return null instead of a coffee, right? And so we just augment the type and we say we're going to return coffee or null. Okay, or you can use an either type or a maybe. Okay, so that's augment the return type. Another thing we can do is we can constrain the arguments. So we can say, well, the size, before you call this function, you gotta check that the size of the coffee is not the size you're passing. Okay, so that's restricting the argument types. And finally, this other choice is to kind of change the meaning of the function. So the meaning before is set size. Well, if it's already set to that, how can I set it? It doesn't make sense. Well, we can relax it and say, well, set size really means set the size or leave it unchanged if it's the same. I should mention there are languages. I know it seems weird that I'm like saying that this is a choice, but there are languages that that like Python, for instance, that do one of these weird choices of like returning null in a certain case or um, don't return the thing unchanged. To me it seems very weird. Like if you say take this string and replace all the x's with y's and there's no x in the string, like just return it unchanged, right? But there's some languages that'll be like, no, I didn't find any x's, so that's an error. I just want to say that's a choice. You can do that. I don't like that choice, but we have to remember that it's always there. Okay, so there's three things that we can do. We can augment the return. Problem with that is it creates this new weird return type. We have to handle the return. So if you return null instead of a coffee, we have to check that. We can restrict the arguments, but in somewhere, something is going to have to check that coffee.size is not equal to size. If you can figure it out with your type system, if you've got something like an Idris that has types that can look at the values, sure, you could do that. Maybe you have some kind of runtime check somewhere, but you have to do it somewhere. So it's kind of putting a burden on the caller again. Change the meaning. That's the best way, but it's not always possible. And then just, something I'm going to recommend is like avoid throwing errors. The more total your functions are, the easier they are to compose. That's a big problem is people will write code that doesn't compose because something in there is throwing an exception. And it's not clear how to put two things that throw exceptions together. Okay. We still haven't, that was just a concept we had to talk about, the operations and signatures, writing out the signatures. But now we have still got to figure out, are we going to use an array or an object? So let's go talk to other people. Can I get my slides back, please? So let's go talk to the barista. They have an operation. So they need to be able to figure out how many add-ins. They need to leave space at the top of the coffee so that they can pump, syrups and soy shots and whatever in there. So they need to know how many add-ins are in this coffee. And in particular, they also want to know how many I'm at the soy station. How many soy shots do I put in right now? So they have this operation that they need. Marketing is going to want to use these orders that we're writing down, and they are asking, well, I don't care how many soy shots are in there. I just want to know how many coffees have soy at all. Is soy popular? And so to do this query, they're going to need to know, does this coffee have this particular add? Finally, the cashier is saying, hey, I need to tell the customer the price. So I need to take a coffee and turn it into a price. So there's all these operations that need to be done based on the different users of this data. Okay, so we can use these signatures of operations, and even in our heads, I can't do it in my head on the slides, like that doesn't make sense, but I can do it. I can write down what's in my head without actually implementing these things. We can see, look, if I have to implement how many add-ins, I'm going to do a filter and get the length. So I'm going to look for all the add-ins of type that are equal to add-in, and I'm going to do dot length. That's going to be a linear search. No matter how I implement it, it's linear in an array. Now, if I'm using an object, when I implement that, it's actually really fast. It's just a constant time lookup, and then with a default of 0 if it doesn't exist. So that's a little tidbit of information that's helping us make this decision. Maybe object is a winner here. Let's look at one of the other operations. So we have has add in, and again, we're doing this linear search using index of, and we're seeing if it's -1. Versus if we use an object, we're just looking up the add in, and if it comes back 0 or undefined, we just double bang it, and that turns it into a Boolean. So this is also, again, constant time. So in my mind, I'm starting to think that object is better. And we used a different lens to constrain this. So we weren't just evaluating on fit. We went to a different lens and started looking at it that way. All right, let's look at the final lens called volatility. So volatility is basically change in requirements, your model changes, your domain changes, the business needs to pivot, do something else. So we can ask, okay, I need to rant a little bit. Right now in software design, we have this fear of change. We think that change is maximal, meaning it's everywhere, and that is unpredictable. But and it's true that there is some change that's unpredictable, but so much of the changes that our business is going to require of our software are predictable. And we don't need to add extra levels of indirection all over the place just in case something changes. I think that's a really bad habit that our industry gets into. But we do need more information, and the best source of that information is the domain itself. So we ask the business, how often do the sizes change? You've been running this company for 20 years. Like, how often does it change? And they say, like, never. We've always had 3 sizes. Like, maybe in 10 years we might change them. It's not worth even thinking about changing them right now. So Okay, that's good to know. We ask the business about the roasts, and they say, yeah, it's we added raw once, 10 years ago, but we don't have plans for changing anything um, in the near future. So like, don't even think about it. So there's no, I mean, basically we consider it never. But the business does change sales and promotions. They have seasonal changes, they have monthly promotions, even weekly sometimes. And so those are going to need to change more frequently than never. And then what about add-ins? Well, it's complicated because there's seasonal add-ins. So like in the fall, we do pumpkin spice, and in the around Christmas time, we do peppermint. So they have these seasonal ones. But then you ask a manager of a shop and they say, well, sometimes we run out of almond syrup and we don't want to sell it anymore. So we want to remove it from the web interface. So, there's this change that's happening hourly. Like as we run out, we need to remove it so that it's not in the interface anymore. Okay, so we can plot this the frequency of change between decades and hourly. And you can imagine it also goes off to the left all the way to never. And we can put our different icons in there. And what we want to do is align these uh, frequency of changes with our development cycle. If something's never going to change, just write the simplest thing and hard code it, like hard code the three sizes as a type and commit it, deploy it, done. But if you hard code the um, add-ins, well, you can't change them hourly. You can't deploy hourly based on every shop in the world changing their inventory levels like that. So we need to think about how this is going to work. And it's too hard to think in terms of like, decades and years and seasons and stuff. So I just bucket it into three different things. So stuff that never changes, we just close it. I'm bucketing called codes. This, if we need to change it, if something changes that we couldn't predict, it's going to require code change and a deployment. And we're betting that that is so infrequent that that's fine. The developers will just like add a size to that type and then everything will be fine. There's open, where you know that you're going to need to change this, but not that frequently, when you just have to add new code. So you're not having to change existing code. You can add a new promotion type. Maybe it's a new class that implements an interface called promotion, and you just code that class, and it doesn't affect any of the other classes that are promotions either. And then finally, we have runtime. So this requires no code changes. They're just values that you stick in a database or in memory somewhere. And the trouble is you don't get any type safety from that because they're just values. They're going to be strings, but but the nice thing is you can store them in the database and then you can query the database. This is these are the add-ins we have right now. Okay, so this is just an example of closed. You just hard code this type with three different strings. Open, one option. Again, I'm just going over one option. You have to look at the particular language you're using, that you're implementing stuff in, and use that to you look at all the features that your language gives you and how do I encode this. But in TypeScript, we can do this. We can have an interface with different classes. Notice we can add a new class that implements the size, and we don't have to change the old ones. And then finally, there's runtime, and we can just say size is a string, and we'll just get it out of the database. Of course, maybe you want something more structured. You're going to have a size, a name, and a price, and other things. Also, though, it just comes out of the database. not saying you have to use strings, I guess is what I'm trying to say. Okay, so let's review. We went over data modeling. Data modeling is about encoding relationships that you have in your model. We evaluated the fit of different encodings. We looked at operation modeling. We talked about function signatures and how useful they are for talking about different use cases. I suggest you use total functions, so don't throw. The implementation complexity is not just big O of N. It's also how hard it is to implement. How complicated is the code to write and understand. But also it has to run on a computer, so that might be important as well. And then volatility modeling, we're going to bucket our changes that we can predict onto these things. We're making bets. This is going to change never. This is going to change frequently. And that will help us figure out what we're going to use to implement it with. All right. And then again, I just wanted to show this model of the process. We take our domain, we're abstracting it into a model that's in our head. We encode that model, and we can evaluate the code to see if it fits our model. So we can run tests against it. We can make a little prototype. We can write a little simulation of a scenario, and then we might find that our model is not right, it's not good enough. We have to go back to our domain and abstract again. Here is my website. I am writing this book, and if you want to sign up for my newsletter, you'll get updates about when chapters come out. My plan is to publish it a chapter at a time on my website for free. So if you want to follow along, sign up. And there, I have to put this because I used the coffee cup image and it required a license. So thank you. That's it.
Thank you very much, Eric. Thank you very much
Thanks,
for an interesting
Magnus.
talk. We had some in the chats shouting, I would go with arrays. I would go with
Awesome.
Yeah, it's nice.
Good, got some participation.
Yeah, very nice
So,
presentation. How come you came into this type of like thinking? When did you start, like your coding journey? Did you just jump off into HTML or Python or something, and then you stumbled
oh,
upon
my whole
there has to be a better
coding
way?
journey.
Yeah.
Oh. Okay. Well, I always liked program. I'll tell a story. I was into programming from an early age. I remember doing logo when I was like 8 or 9 on like Apple IIs we had a computer lab at school.
Mm.
And in high school, I was really into Unix. I ran Linux, and I was reading an article by someone who said that engineers, programmers, um, and in their informal poll, they found the writer of this article found that people said that they liked the program because they liked the control. They liked that they're making like this intricate watch, like and having to make everything work correctly and together. And when I read that, I thought that doesn't sound like me at all. That's not what I'm into. I'm into the expression of ideas, and programming is a way of expressing your idea in like a formal way. It has to run, has to compile and run and do the right thing. And so when you find that it doesn't do what you thought it would, you have to, if it's not just a typo, right? It's something like, oh, that didn't work the way I thought it should. You actually change the way you see the world, you see the domain. And I love that process of learning by creating a thing. In the same way you might make an architectural model and feel, oh, these two will never fit together, right? I need to change the walls here.
Mm-hmm.
Is it the same kind of process? And so when I've been programming on teams professionally, I realize a lot of people aren't doing that. They are thinking more like, I'm making this cool machine that's doing all this work. I'm like, yeah, but you're not expressing the ideas. Like you're not, you know. So anyway, just talking with people and um, gaining experience myself, working in different domains, I realized this isn't common. This isn't common knowledge. People focus so much on the code. They want their code to like, we talk about clean code or we got all these refactorings that, move code around and organize it better. All that's really important. But we're not talking about like, what does the code represent? What is the semantics of it? What does it mean? What does it do? Like, is that really what we want it to do? And I find that the more you can encode the domain into a good model, the better design your software will be. Like instead of trying to like clean up your messy code, like it's sort of like cleaning up a room. Like, yeah, you can put all your toys away, but are those the toys you really want? That's a different question, right? So, yeah.
Yes. Well, thanks. Yeah. Have you ever worked with app or function that's never changed? The customer comes or someone comes with this is the requirement list, the box. It will never change.
No, no. But I'm also not afraid of change.
No, no.
Like I don't know why, so I do know why. I do know why. I mean, this is my hypothesis for why
Yeah.
we fear change so much,
Yeah.
or why we try to put indirection in
Mm,
to to make change easier when we have no reason to suspect it'll change. It's just fun.
mm,
Um, so let's say we put in 100 indirections and one of them hits. It feels way better. Like it feels so good that we like didn't have to change anything. We could just like add a new line here and like, oh look, now we have this whole new feature. It's changed. It feels so good that we forget that it cost 100 times because only one of them hit. And so it's kind of like this gambler reflex. Like gamblers don't remember how many times they lose.
no.
They just like the feeling of winning so much.
Yes.
So I feel like it's that we get the hit so hard that we are willing to put all this work. There's this whole phrase of like, why write 10 lines of code today to save 10 lines of code tomorrow, and that tomorrow may never come.
Mm,
Like,
yes.
just write the thing straightforward and then use Git, use your code editor and delete the code and write new code. Like, I don't understand why we have to fear it so much.
Oh no, no, me neither. I'm just curious. I agree. I never worked in a project where things hasn't changed.
Yeah.
Especially
Yeah.
people come and say this is the final draft, or not final draft.
Oh,
This is the
right.
final. We know it's the final. We start developing, and then it goes a week or two, and then oh, by the way, we're gonna tweak this.
And, well, I mean, also like an interesting discussion in itself.
Mhm.
Like, I mean, in some situations, in some scenarios, I would just call that unprofessional. Like you asked us for X, we estimated it, and now you're asking us for X plus Y.
Mm.
Like we have to start over. Like
Mm.
let's start negotiating again.
Yes.
And if we were maybe a little tougher on them,
Mm.
instead of saying, yeah, I guess that's possible, and we do that for Y and for Z, and we just keep doing it, like eventually they're like, well, why is the system taking so long? And we're like, well, you did all these changes. Well, I asked you if you could do it. You said yes. Like
Yes.
it's our fault, right?
Yeah.
So I think they're being unprofessional. We're being unprofessional, and we should maybe be tougher.
Yeah, I usually tell people, or especially business people, and like never ask software developer if it's possible to do, because they will always
Right.
answer yes. It's always possible.
Yes. Exactly.
It's like
Right. Do you mean wait, possible and on time and on budget?
different
And
stuff.
yeah.
Different. Possible, yes.
I'm the same
Always.
way. I'm the same way.
It's always
I
possible.
had a manager who asked me, hey, can you do this? I would just pass by him in the hallway and he'd say like, hey, do you think you could do, how long do you think it would take to do X? And be like, oh, 3 days.
Hmm?
And He's like, okay, have it by Tuesday. Like, whoa, that is a different. That's not what I was answering. And not like from now, like from this moment.
No.
Like I meant like the amount of work it would take is 3 days of work, not like I have stuff to do now. Yeah. But yeah, that kind of thing you have to check.
Yes. Thanks. Yeah, people in the chat are really happy.
Oh,
Thanks for an
that
interesting
makes
talk.
me happy.
Yeah.
I yeah, because I sometimes worry, I have anxiety about whether people like the ideas or I'm hitting all the right
Yeah.
ideas. It's good to hear.
One final question. I
Sure.
guess you're gonna put out the presentation somewhere on your page, so we'll link to it during the or below, not
Yeah,
below the
for sure.
movie here, so you can find the link to his presentation. If
Yeah.
you're interested in looking at that, yeah. With
Yeah,
that,
I'll email you the
yeah.
presentation.
With that, thanks again, Eric, for coming to Prog Sweden. Thank you very much. It was very nice presentation. I liked it a lot. It was a lot of
Thanks, Magnus, and
not so
thanks
much
everybody
coding,
watching.
more like thinking and, as you said, like code, think, brain, yeah, concepts. Thank you very much again.
Yeah.
Thank you.
Thanks.